Hi, my name is Tarun Alwala, and this is my Lab 3 circuits. So the objective of this lab is to analyze and predict circuit behavior involving series and parallel resistors, measure current voltage using multimeters, and investigate how resistors and capacitors function within a circuit. So the tools that we used were multimeters, resistors, wires, and capacitors. And the graphing software that I used was Excel. And the system versus surroundings were the components inside of the circuit versus the external environment. And the results were that the node and loop rules hold true throughout the experiment. So let's talk about the fundamental principles that were involved in this lab. The first is Ohm's law, which is just V equals IR, or the voltage equals to the current times the total resistance inside of a circuit. And then next is the node rule, which is the total current entering a node is equal to the total current leaving the node, basically conservation of charge. And then the third principle is loop rule, which is that the sum of all voltage changes around a closed loop in a circuit equals zero. And this is a result of the conservation of energy. These are just some pictures from our experiment setup. And as you can see, we just have a battery source of 3 volts in the wires, and just the multimeter is connected to wherever the experiment specified. And then let's talk about how to calculate the total resistance in the beginning. So since the series is just in since the circuit is just in series, I just added uh, the two resistors. So it would just be 47 plus 100, so 147 ohms, and the total current would be 3 over 3 divided by 147, which would be 0.02 amps. And next, what if the ammeter connections were reversed? Nothing changes, the current stays the same throughout the both of the ammeter readings. Now, what if the ammeter was replaced by a voltmeter? The ammeter reads zero because the voltmeter has a very high resistance, which actually prevents a significant current from flowing through a bench. The voltmeter reads 3 volts because there are no other voltage drops in the circuit, so the entire voltage appears across it. So let's talk about the voltage drops across each component. So we have the equation where VB minus the voltage drop across the 47 ohm resistor and minus the voltage drop across the 100 ohm resistor equals 0. And then the next 3 lines just consist of the change in between each of the individual segments. So AB has a change, CD, and EF. And the other segments involved do not have any change in voltage between them, so it's the same potential. So why does the voltmeter change the circuit, but the ammeter doesn't? As I mentioned before, the voltmeter has a high resistance, so that there is only a minor amount of current flowing through it, and it can also be depicted through this graph as well. And if the ammeter is replaced by a voltmeter in parallel with a 100 ohm resistor, what happens to the current through that ammeter? The voltage drop would be zero across the branch with no resistance, so the current would just be 3 over 47 amps or 0.02 amps approximately. So what would be the resistance through each element? It would just be the voltage difference divided by the current. So for 47 ohm, it's actually 48 ohms, and for the 100 ohm, it's 102 ohms. And these are not accurate in the sense because the current utilized was rounded up, and there's no resistance throughout the rest of the components. This is our setup for the capacitor and resistor circuit. And this is just my plot that I derived from utilizing the stopwatch to count the charging and discharging time. And also, I calculated the voltage differences. And the predicted would be 6, but the experimental value I got for the capacitor value was 5.87. So there was human error using the stopwatch during capacitor and charging and discharging, in the sense that we might have mistimed just a little bit. And there was also error while measuring values inside of the actual circuit using the multimeters. And there might have also been some possible degradation of circuit elements as well. So let's talk about the conclusion questions. The first one is, what would happen if you charge a capacitor with no resistance in the circuit? So in an ideal model, the capacitor would charge instantly because RC equals 0, and in reality it would not charge instantly since all circuits have some amount of internal resistance. And second is, why is the measured charging time different from the predicted time? The measured time is longer because real components have internal resistance. This added resistance increases the time constant and slows the charging process. Thank you for listening.